All right, today we're going to talk about U-substitution. If you guys can turn to page 7, spend a minute to just copy down the notes, the additional notes that I have up here. Page 7. Okay, so far, we've been just focusing on power rule. I mean, we've done a little bit of trig integrals, but most of our process has just been doing with power rule, right? And with power rule, we know that the majority of the work is, for us, has been trying to get a problem ready for power rule, right? We had these restrictions that were in place in order for us to use power rule. Variable had to be in the numerator, radicals converted to rational exponents, and if we see any parentheses, we have to make sure we resolve them, expand everything out, distribute everything through. Okay. So today, we're going to be talking about a process where power rule alone is either not going to be very efficient or impossible, just based off of order of operations and being able to put get our conditions to pass. So U-substitution is the reverse of derivative chain rule. We basically want to look for a function and its derivative to be in the integral. So U-substitution is a method of rewriting an integral problem into a simpler one in order to help us identify an integral rule that's appropriate for the problem. Okay. So right now, we only have a couple of rules available. Most of it is going to be power rule that we're going to try to get it to look like. So all these are in terms of U, basically setting us up for U-substitution, right? The idea is that we want to get a complex problem to look like this so that we know exactly what rule is available for us to use. Okay, and U-substitution is a process of undoing chain rule for derivatives. Okay. Here's a quick example. Imagine I had a function of sine of 3x. The derivative would be cosine of u times u prime, which will be 3 cosine of 3x, which means that the antiderivative of this must bring me up to sine of 3x. But if you look at this left side and you're asking yourself, okay, I know cosine becomes sine, but how do I know that this 3 is going to disappear and is going to produce sine of 3x, right? We can get to it from f to f prime, but then going from f prime back to f of x, it doesn't seem as easy to identify. So we need some help, and the help is going to come in this in the form of this u variable. This u variable is going to be kind of like a temporary variable. It's going to kind of hold us, kind of help us organize information in a way where it's easier for us to know what's needed and what needs to be in place to bring us back to the original problem. This doesn't seem like a big deal with that 3 here. It looks like that's something that, we know cosine becomes sine x, and then that 3, we just have to kind of figure out what to do there. But I want to show you something that's like a more involved chain rule where we feel like, okay, we definitely need some help. No need to write this down, but this is just what we did at the end of last semester. Chain rule for derivatives. We handled trig problems that were much more involved. The sine of 3x to the 4th power, right? We get that 4 to be rewritten using brackets. And then we have to identify, okay, this is chain rule, but there's 3 different layers to this problem. There's that bracket to the 4th, there's the sign of parentheses, and then there's that 3x, right? And then we take turns and find the derivative of each with their own separate space. And then once we get that all filled out, we fill in the bracket and the parentheses with the original parts. And once we're here, we want to clean up, right? So 4 times 3 is 12, make that sine cubed 3x. So this is the derivative, right? I mean, once we knew what to do, it didn't end up being too hard, and most of you guys showed you were able to get to this through this process without too much difficulty. But this is the derivative, right? But now that means that if this is the derivative, that means the antiderivative of this must bring me back up to the sine 4th of 3x. But imagine having to start here and trying to work your way back through to this original part. Like, how do I know to resolve that 12? How do I know that 12 disappears? How do I know that there's that cosine that's needed to produce that? Right, so we need some help. So this temporary variable U-substitution is going to allow us to know how to work backwards, because it's not as straightforward going backwards as it is from going from here to the derivative. Okay, so that leads us to what we're going to be trying to do with today's notes. Right. Now there are steps for U-substitution, but I'm just going to run through the steps after we start the example. Okay, so I'll point those steps to us. I'll point those steps out as we work through our example. Okay, so here's example 2 on page 7. Integral of x times x squared plus 1 to the 15th. Okay, so imagine that the only rule that we have so far is power rule. Okay, what would be the challenge of using power rule for this problem? Got to expand it all out, right? Imagine having to do that 15 times, right? You got to parentheses, fill everything out. Remember, 15 parentheses, expand it all the way out, and then get it all cleaned up, and then do power rule. That would just take too long, right? It's possible, but we want to have a more efficient way of doing that. And also, we can't just distribute this 15 through, right? Order of operation doesn't allow us to just distribute that through. We're breaking rules if we do that. So we want to find a more efficient way of working through a problem. Now, having said that, we always want to explore power rule expansion first. That should always be the first option. But we should be able to quickly tell by looking at the problem whether power rule and expansion is an option. If it's not, whether it's too complicated or it can't be done, then we move on to our second option, and our second option is U-substitution. Okay, U-substitution is reserved for more complex problems that power rule can't handle, or expansion through power rule is not going to be able to solve. Okay, so I want to keep reminding us of that, because as we do more and more U-substitution, we're going to begin to think that U-substitution is going to be the first option anytime we see a problem. But we always need to consider expansion first, because if we don't, then we're going to get stuck thinking it's a U-substitution problem. It's a lot harder to kind of work backwards and realize, oh wait, it's not a U-substitution problem if we're always considering that as the first option. Okay, so here's what we need to do. We know expansion is not going to it's not going to be very useful for this problem. So let's go to U-substitution. So here's the first step. Assign the U value to be the expression inside the parentheses. Okay. This is more of a rule of thumb. It doesn't mean that every parentheses we see is going to be the U value, but at least to begin the process, that's where we look. Okay, the expression inside the parentheses. So There's our u value right there, x squared plus 1. So I want you guys to underline the x squared plus 1 portion inside the parentheses, and I also want you to underline the dx. These are our priorities. We're going to substitute these in terms of u in the hopes that we can make it turn into a rule that is available to us. Okay. All right, let our u value be x squared plus 1. Next up, it says find the derivative of u. All right, so derivative is not going to go away, and this semester is all about integrals, but derivative is going to play an important role as we go through our integral process. So we want to get that dx replaced as well. To get dx, we have to find the derivative to get that dx to show up. So we're always going to find the derivative of u. So du over dx means I want to find the derivative of u with respect to x. So what's the derivative of x squared? 2x. What happens to the 1? 0. Okay, so du over dx equals 2x, right? Now we want to solve for dx. To do that, we're going to cross multiply. If it helps, you can put it divided by 1 to kind of show where the numerator and denominators are. We're going to pair the diagonals with each other. So we'll say 2x dx equals du. Okay, we're working towards isolating dx so I can replace that second piece I need to be there. All right, I want to solve for dx. What can I do to solve for dx? Divide by 2x. All right, so my priority is just replacing what I underlined, the parentheses and the dx. Anything else, we're just going to bring back into the problem. That will not be replaced, and we're just hoping that the x will go away on its own. Okay. Parentheses becomes u. Don't forget about the 15. And then dx gets replaced with du over 2x. All right. We're getting closer to our goal. The x's cannot be there if we want to do U-substitution. Are the x's going to go away here? Yes. There's a numerator x, there's a denominator x, there's no addition, there's no subtraction that's preventing us from canceling those out. So those can go away nicely. There is a leftover what? 2. There's a leftover 2, which is okay. Okay, it's okay to have leftover coefficients, we just can't have any leftover variable x's. Where can I put that 2 to kind of separate it from the rule that I want to use? Yeah, let's push it out in front to kind of get it a little bit more organized. We're keeping track of our coefficient, but we know it's just not going to play a role in changing and applying power rule. Okay, are we good so far? Okay, now I want you to look at this here. If you were to cover up that 1/2, it should match exactly with the rule that you want to use. Okay, so that needs to be the case every time. If you want to go do substitution, once you get everything cleaned up, if you were to cover up the coefficient with your finger, it should match exactly with the rule you want to use. Not anything, there's no changes, there's no slight change, there's no multiplication with another variable. So I want to keep reminding us that our integral rule is very restrictive. Okay, it needs to match exactly. If it's not an exact match, we're not going to be able to use it. Okay, it's not something that that we can. It's not very flexible. Basically, these rules are very inflexible. If you can't get a perfect match, either you can't use it, or we got to find a different way. Okay. All right, so this matches perfectly with the rule that we want to use, power rule. Okay, what did use to the 15th turn into? Over 16, right? The 1/2 stays in front. The integral and du notation goes away. In place of it is the antiderivative and the plus c. Do a little bit of cleanup here. 2 and 16 can multiply to be 32. And now, next to last step here, write the answer in terms of x. So u is only a temporary variable. We used it to help us see what rule we can apply. But now that we've done the work, we're going to bring our answer back in terms of the original variable that we started with. So replace the u back in terms of x. We have our answer, but we just want to bring back our permanent variable. So this process is a lot more efficient than having to expand this x squared plus 1 15 times, FOIL everything out, combine like terms, do power rule for each term, and then factor it back to look like this, right? Much more efficient way.
Why not distribute the 1/2 to the c?
Yeah, it's a good question here. The reason why, technically, yes, we're distributing the 1/2 to the c, which would become c over 2. But what's c over 2? Right, it's still a constant. Yeah, 1/2 times c is still a constant. So any constant multiplied with a c will just get absorbed into that plus c. We don't have to keep track of it. We can just leave it alone. Okay, questions with 2. All right, example 3 here. X squared, secant squared, 2x cubed. This looks like a complicated problem. We look at the rules available. Okay. Looks like we can move towards maybe secant squared, right? If we get it cleaned up, maybe we can apply that rule. But I want you to look at this something here with me as well. Maybe you're looking at this going, oh wait, that's a secant squared and that's an x squared. So I'm going to take 2 rules separately, right? Do power rule for x squared and do secant squared into tangent u. Okay, we can't do that. Okay. Again, anything that's multiplied, we can't separate into individual rules. It's stuck. If it doesn't match a rule, then we have to make it turn into a rule that we can use, right? We can't separate with multiplication. Again, these integral rules are not as flexible as you would like, okay? So we have to go through U-substitution. To go through U-substitution, we have to assign the u value to the expression inside the parentheses, okay? What's the u value here? Okay, so go ahead and underline the parts that we're going to focus on. We're going to replace the 2x cubed and the dx. Everything else we're going to bring back into the problem. Our focus is just those 2 to begin with, and we'll deal with the rest later. Okay. After you find the u value, you always want to go ahead and find du dx. You always want to find the derivative. Okay, what's the derivative of 2x cubed? 6x squared. If you want to put a 1 underneath, just so that you can see where the diagonals are going to be paired. Next up, we want to solve for dx. Let's make our way towards that. Cross multiply, 6x squared dx equals du. Solve for dx. And we're just going to substitute what we underlined in red. Everything else, bring back into the problem. Okay, we keep checking here. Looks like it's getting closer towards a rule that is available to us. What can we do still, though? Yeah, if the x's cannot go away cleanly, we have an issue. But in this case, x squared matches up, goes away nicely. There's still a leftover what? 6 we can push out as 1 6. Okay, it's okay to have leftover numbers. We just have to keep track of it, but we can't have any leftover x's. Or if we did, we either we went down the wrong path, or we have to resolve it down the line before we can apply these rules. Okay, 1/6 comes out. Okay, do we have a perfect match? Yes. If you cover up that 1/6, it should look exactly like the rule you want to use. Okay, secant squared becomes tangent u, 1/6 tags along. Okay, we're almost done. What's our final step here? Yeah, remember u is only a temporary variable. You want to bring your original variable back into your answer. Okay, questions so far? Okay, example 4. It's another problem that we have to maybe consider power rule first. Can I expand this using power rule for number 4? All right, we can't distribute x cubed through a radical, right? We're going to break some rules for order of operations. So we're stuck. We tried power rule. It doesn't work. Examples 2 and 4 are problems where expansion is, we don't want to expand for different reasons, right? This one, we don't want to expand because there's too much hassle. It's not efficient. This one, we don't want to expand because we can't, right? We just don't have the option to even do that. So either way, though, we have to go through U-substitution. To get the U-substitution, though, we want to assign the U value to the expression inside the parentheses. I don't see a parentheses here, but can I create one without changing my problem, without changing the value of my problem? Yeah, radical, convert it, right? Let's convert that radical to parentheses to the what power? 1/2. Okay, now that I have a set of parentheses, I know where to go for my U value. As soon as you find your U value, you're going to do du dx. Okay, what's the derivative of 5 minus x to the 4th? Yeah, negative 4x cubed. The 5 as a constant goes away to 0, right? Only this second term remains. If you want to put over 1, you can. Cross multiply. We're going to work towards trying to get that dx by itself. Okay, solve for dx. Right. Substitute the parts that I underlined in red. Are the x's going to go away cleanly for us? Yes. There's leftovers though, right? What's the leftover? Negative 1/4. It's okay. We can have that in the problem and still be able to move forward. We just don't want to lose track of those. Okay, if you were to cover up that -1/4, the perfect match, right? Got a perfect match. There's nothing attached to it. There's no multiplication of anything else. There's no x left over. And also, I see some students do this where there's a leftover x and they push it out as a coefficient. Okay, that doesn't work. Okay, you can only push out coefficient if it's a numeric value. If it's a variable, that's an issue. We can't move forward until all the x's are gone. Okay, so do a power rule here. -1/4 stays. U to the 1/2 becomes U to the 3/2 over 3/2, and then plus C. Let's get that 2/3 in the denominator to flip up to make it easier to clean up. 3/2 in the denominator becomes 2/3 up above. -2/12 becomes -1/6. Bring the U, bring the 5 minus x to the 4th back, and then plus C. Oh, yeah. Okay, any questions so far? Okay, before you guys flip to the next page, I want you to observe something here with me here. I want you to look at all the U values. What is it about these U values that allowed every problem to get all the x's to go away so nicely and cleanly? Can you look at the problem and see why we're able to get all the x's to go away so nicely?
The exponent is 1 degree higher in
One.
U than it is for the
Right. So whenever you see your U value being 1 degree higher than the leftover x that you want to go away, that's a good sign because you know the derivative is going to push that exponent down 1 degree, and that will handle that x, right? Leftover coefficient is okay. You know x squared becomes 2x. That x is okay. It's going to match up with that x. 2x cubed becomes x squared and x squared. That's going to pair up nicely. X to the 4th becomes x cubed, that matches up nicely. So if you were able to see that pattern, it kind of gives you a hint as to how the problem will work out. You know that it'll be an easier problem. When you see that, it's a good indication that, okay, I'm along the right path. We are going to see some problems where we're going to see some roadblocks ahead because the degrees are not going to be favorable. It doesn't mean that it's not going to work. It just means that we have to prepare for working more to try to get things to resolve. Okay. But it's just want to point that out to you that sometimes you can look at a problem to quickly tell, okay, it's going to be an easier problem or is it going to be something that's more challenging? Okay. You see that degree relationship between the U value and the leftover x. Okay. All right. Next page. Okay, sometimes a challenge for a U-substitution problem is one where the U value is not very apparent. Okay, if you look at this problem here, this doesn't look anything like, or it doesn't look exactly like any of the integral problems that's available to us, right? Maybe you saw something that looks familiar. Maybe you're looking at this going, oh wait, I see a secant squared, so can I just apply secant squared? I can't because it's attached to tangent to the 5th x, right? We can't separate problems if it's multiplication. Okay. Either it looks exactly like it or it's not going to work. Okay. So we know this is too messy for any rule to handle, which means we got to go through U-substitution to hopefully break this down into easier problem using a temporary variable. But to do U-substitution, we got to create parentheses. Okay. And looks like we could create 2 sets of parentheses. And because of that, we may have to kind of pick and choose which one is going to be the correct U value. But first, though, How can I write these as parentheses? This I can write this as what? Tangent fifth x, the same thing as. And then secant squared x, the same thing as x squared, right? So at least we get the parentheses to show so that we can look at some options available. It's either tangent is the u value or it's either secant. Okay. So before we jump and commit to one u value, let's just kind of look ahead, right? We know the derivative of tangent is secant squared. We know the derivative of secant is secant tangent. So which do you think would be the better fit? Yeah, if our u value is tangent, it'll produce secant squared, which will match up nicely. But if we let our u value be secant, the derivative will be secant tangent, which pairs up slightly, but not perfectly, right? That fifth degree is not going to pair up with that tangent of the first degree. One of the tangent goes away, but not everything goes away. We're trying to find that perfect fit. And that perfect fit is going to come from this u being tangent of x, okay? So that's what I'm going to commit towards. Tangent x being the u value, and we're always going to find a replacement for dx. Okay, so we start there, u equals tangent x. Okay, du over dx, secant squared x. Okay, put that secant squared x over 1. If I cross multiply, I can work towards getting that dx to show. Okay, solve for dx. Let's divide that secant squared over.
It always should be du over whatever the derivative is.
Yes. But sometimes it's nice to get into the habit of doing this, especially when there's like negative exponents involved and fractions involved. But yeah, for easier problems, you can jump a little ahead without going through everything. But I want to show you everything in case it's messier and you want to kind of have everything lined up. Okay, so let's make our substitutions, right? Replace the tangent with u, replace dx with du over secant squared x, and copy everything else that's not underlined. All right, are we able to get the x's to go away? Yes, secant x squared is the same thing as secant squared x. One is in the numerator, one's in the denominator. There's no addition and subtraction getting in the way. Those can pair up and go away nicely for us. No coefficient to keep track of. This will be a straightforward power rule problem. This matches perfectly with the rule that's available. And now we can jump into a power rule. U to the fifth becomes okay, we're almost there. What's our final step? Yeah, bring that tangent back in. You can either leave that 6 in the denominator or you can push that 6 out in front. My preference is to push it out in front. Just if there's anything else that we need to do to it, it's just nice to have that coefficient in front, but it doesn't matter as long as your variable is back. Okay, take a look at number 6. Is this problem possible using just power rule expansion? Okay. Is there anything that's preventing us from being able to merge those things together? The radical is the denominator, but there's only one term, right? We could bring it up as what? Y to the negative 1/2. We can distribute that through. There's only one term. It's okay. If it was like square root of y plus 1, right, that's a different issue. But there's only one term. This is okay. This, I know the parentheses is kind of misleading us because, okay, that could be, these could be u values, but it's actually going to be a power rule expansion problem. Okay, there's nothing getting in the way, right? There's no messy exponent. There's no ugly radical with multiple terms inside of it. So this is a problem where it's going to be a expansion power rule problem. So I want to keep reminding us that whenever you see a problem, always consider power rule and expansion. Can I just move terms around and rearrange it and separate everything out so that I can rely on power rule? Only reserve the more complex problems that power rule would run into for U-substitution. Okay. Otherwise, if you try to go through U-substitution for this, you're going to get stuck because there's not going to be a U value that's going to allow things to clean up. Okay, so always consider power rule as your first option. U-substitution is your second option. Okay, so you can either bring this up as y to the negative 1/2, or you can just put this in the denominator and then separate them out individually later. Okay, I can split this up into individual fractions. There's only one term in the denominator, so it allows me to do that. Okay. We want to get this ready for power rule. I can bring this y to the top, make it y to the negative 1/2. What happens to the second term? How can I resolve this? I can subtract exponents, right? 1 minus 1/2 is 1/2, so y to the 1/2. So in my cleanup stage, I haven't done any calculus yet. I'm just rearranging it to get it ready for power rule. No U-substitution needed. Okay, so now we're ready for power rule, right? Add 1 to the exponent divided by that new exponent. Negative 1/2 plus 2 over 2 is 1/2. One half plus 2 over 2. 1/2 plus 1 is 3/2. Flip those fractions up. 1/2 becomes 2 in the numerator. 3/2 becomes 2/3 in the numerator. So 2 times 3 is 6. Okay. Any questions so far? This is an expansion power rule problem, no U-sub. And the only way that we can tell is we always want to test it out, right? Test out, can I just move things around and get it ready for power rule? If you can, that's the method you want to do. You don't want to rely on U-sub as the first option because you may get stuck not being able to move forward because it's not designed to be, there's no need for U-sub. Okay, I want to start this next topic here. This is change of variable U-substitution method. Let's just approach this problem like we normally would a previous problem, right? First step, can I expand this? Can I just distribute that x through? No, order of operations, we can't do that, so we're stuck having to go through U-substitution. If I want to do U-substitution, I need to create a set of parentheses. Can I see a set of parentheses here? X plus 3, okay. Okay, we know what the target for our u value. We know our dx will be replaced. All right. Do you see a potential issue as we move through this process? Yeah, the degree is not favorable, right? This x is not going to produce anything that's going to match with that degree once the derivative is taken. That just means that, okay, we have to be aware of that, but we can still move forward. Just have to find a way to work around that issue. And we'll talk about that when we reach that point. Okay, let's find the derivative. Du over dx equals 1. X goes to 1, 3 goes to 0, cross multiply. Okay. Go through our substitution steps like how we normally would. Keep the x, replace the underlined portions. Okay, what's the issue here? Okay, x stays in the problem. Okay, now some of you may try to find creative ways of saying, well, can I just do power rule for x and power rule for u, and then just merge them together? Okay, that will be okay if I had a plus sign in between, but these are multiplied. So again, our power rule, our integral rules are very restrictive. If anything's connected through multiplication with something else, it just can't be applied. So I can't do x squared over 2 times u to the 3 halves over 3 halves plus c. Okay, we can't do that. So we have to get that x to be replaced. We have to find a way to get that x to be in terms of u. Do you see anything available to us that can maybe help us substitute that x? Yeah. So this is our creative way of working around the issue that the x's do not go away. This is called the change of variable method. How can I rearrange this to help me substitute for that x? Yeah, if I know that u equals x plus 3, I can rearrange this to say x equals what? U minus 3. So I'm going through a second set of substitution to take care of that remaining x that did not go away by itself. Okay, we still have something more to do, but at least we have something that that we can move forward, right? At least everything's in terms of u, but we're still not ready for power rule, right? What else do we need to do? No more substitution. Everything's in terms of u. To do power rule, we can't have any what? Yeah, we got to resolve the principal. We got to distribute everything through, get everything to be separate. Okay, so distribute that u to the 1/2 through. There's a hidden 1 here. So what's u to the 1 times u to the 1/2? 3 halves, yeah. Remember, this is not power rule yet, so we don't want to drop the integral. We're just trying to do some cleanup here. Now everything is nicely ready, right? X's are gone, parentheses are resolved. Now we're ready for power rule. Okay, u to the 3 halves become plus 2 over 2. One half becomes 3 halves. Flip the 2 halves to the top, flip the 3 halves up as 2/3. I'm going to clean up the coefficients, but I need my u in terms of what? Yeah, remember, u is only a temporary variable, so I still need to bring my original variable back into the problem. The 3's will cancel out. I'm just left with 2. Okay, questions there? All right, we'll pick up with continuing with notes tomorrow. You guys have homework tonight from 4.5.
That's